Hi everyone, and welcome to Calculus Lesson 4.1, Areas and Distances. In this lesson, we're going to talk about how to find the area under a curve using estimation with rectangles. We're going to talk about some of the different strategies we have with that and some of the formulas that are involved. So let's take a look at what we have. So some general formulas we have are formulas for the rectangle's width and formulas for the estimated area. For each rectangle's width, we would need to know how many rectangles we want, the starting point of the interval we want the area of, and the ending point of the interval. So if I take the total distance here, which would be the ending point minus the starting point, and I divide it by the number of rectangles I want, that will get me the total width of each rectangle if each of them is an equal length. Okay, so to find the width of each rectangle, you would do the furthest point you want minus the closest point to the y-axis and divide by the number of rectangles. Now, for the height of each rectangle, you take the x value that's here. If you wanted to use right endpoints, you take the right x value and you put it into your function, and that would give you the height. If you wanted to use left endpoints, you would take the left side of the rectangle, that x value, and put it into the function. And if you wanted the midpoints, you would take the middle value in the rectangle. So you would have to find the middle value. You can average the two x values that make up the ends, and that would get you the middle. Okay, so once you have the heights, if you wanted to find all of the areas, you can add all of the heights together. Okay, and then you can multiply by the widths. Okay, so you can add all of the heights together. This should have been x sub n. There we go. And you would be able to find that estimated area. Now remember, these estimations are not perfect. See all this white area under this curve? That means that I have an underestimate here. Sometimes you'll have an overestimate. But the more rectangles you use, the closer your estimate will be to the actual area under the curve. So if you use an infinite number of rectangles, your estimate is going to be exact because those rectangles will be so skinny that it's like they don't have any width at all. And that's where calculus comes in. So let's take a look at another formula for the exact area under the curve. To find the exact area, we would need the limit as n approaches infinity. Now notice, this is going to look very similar to what we had on our previous slide. We have delta x times the height at an x value, plus delta x times the height at an x value. And you keep adding this together. This is x sub n. If n is infinity, that means that there are an infinite number of terms in this sequence. But don't worry, we have a way of doing that. So don't panic by thinking you have to add together an infinite number of things. You would be there together. Well, forever, basically. So you're not going to be there forever, I promise. We have math to help us out. Now, if I wanted to write this sum in a more compact way, I would use summation notation. This is also known as a Riemann sum. Okay, so that formula that we just talked about would look like this in a Riemann sum. So it's the limit as n approaches infinity of the sum. This sigma means sum, this E looking thing. And then it tells you where the first rectangle is, I equals 1. That's the first rectangle. And it tells you how many rectangles you have. Now, if we have an infinite number of rectangles, this would be infinity. Okay, this is the height of each rectangle times the width of each rectangle. Okay, so that's how we would sum it up using the summation notation. We're going to practice that a lot in lesson 2, but this is just a basic introduction to that notation. But let's do an example to show you how all of this works. We're going to do an example where we have to estimate the area under a curve. In example 3, it says, let A be the area of the region that lies under the graph of f of x equals cosine x between x equals 0 and x equals b, where 0 is less than or equal to b, which is less than or equal to pi over 2. They want us to estimate the area for the case b equals pi over 2 by taking sample points to be midpoints and using 4 subintervals. So what they're setting up is they're setting up the function f of x equals cosine x, and our a value is going to be 0, and our b value is going to be pi over 2. Okay, so this is the furthest to the left the graph is going that we want the area. This is the furthest to the right that we want the area to go. So let's take a look at what's actually happening here, and let's try and figure out some of the values we're going to need for this. Notice we're using midpoints, and we're using 4 subintervals. That means 4 rectangles. The first thing we should calculate is the delta x. Okay, so notice I have my sine function graphed here, the orange line in this picture, and it's from 0 to pi over 2. That's the range that we want. So I'm going to do pi over 2 minus 0, and then divide it by the 4 rectangles that I need, 4 subintervals. So pi over 2 minus 0 is just pi over 2. And pi over 2 divided by 4, I flipped the fraction, so it's 1/4, and I changed to multiplying. So pi over 8 is the width of each subinterval. So you'll notice I labeled this x-axis. This is pi over 8. Pi over 8 plus pi over 8 is 2 pi over 8, which reduces to pi over 4. Plus another pi over 8 is 3 pi over 8. Plus another pi over 8 is pi over 2, also known as 4 pi over 8. So those are my right endpoints, and that's the first thing I usually find in all of these. But they don't want us to use the right endpoints. So I've defined where this rectangle begins and where it ends, but that's not really what I need. They want me to use the midpoint of each interval. So the way you do that is you average the beginning point and the ending point. So you would do 0 plus pi over 8 divided by 2, which is pi over 16. And then for this rectangle, to get the midpoint, I would do pi over 8 plus pi over 4 divided by 2. That gets me 3 pi over 16. Okay, then I would do pi over 4 plus 3 pi over 8 divided by 2. That's 5 pi over 16. 3 pi over 8 plus pi over 2 divided by 2. I'm just averaging those to get my midpoints. Now I'm just going to put this all into my formula. So this is delta x. These are the values I need to evaluate my function for. And remember, the function is cosine x. So we're just going to do that all in a calculator. Let me show you that calculation that needs to be done. In my calculator, I typed pi divided by 8. I put parentheses, cosine pi over 16, close those parentheses, plus cosine 3 pi over 16, close the parentheses, plus cosine 5 pi over 16, close the parentheses, plus cosine 7 pi over 16, close the parentheses. You need to close one more parentheses, and then you hit enter. Of course, you make sure your calculator is in radian mode, and you get 1.006. So that's the estimate for this. Okay, and it should be pretty close to the actual estimate. I would say it's neither an over nor an underestimate. We can't tell from this because notice part of the rectangle is out here, part of it is in here. So it's hard to tell whether it's going to be an over or an underestimate. We know it's not perfect because this is a curve, but it will be close to the actual value. Now, our lesson was titled Areas and Distances. So let's talk about distances next. So if we want to know the distance traveled by an object during a certain time period, if we know the velocities at all the given times, we can simply use the fact that distance is rate times time. So we need to know how long the object was going at a certain rate. Okay, and if we multiply those together, we're going to get distance. Notice this is very, very similar to what we did with areas, where we had the height of the rectangle times the width of the rectangle. Okay, so if our velocities are varying, it's going to be very similar calculations. If we have a constant velocity, we don't have to worry about that. You just do the total time times the rate. And that's not calculus, that's just a question that we did in 7th grade math. but we're doing varying velocities. So they're going to give us a table of values. We're going to find the change in time for each interval. Generally, those changes will always be the same number. And then we find the sum of the interval times the velocity. Okay, so let's take a look at our last example, example 4. In example 4, it says, suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds and record them in the table. Find an approximation for the number of feet traveled in this 30-second time interval. So notice what they've done is they've given us the times in this top row and the velocities in this bottom row. Each time interval is 5 seconds. So we have from 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, 25 to 30. It's always 5 seconds. So that's my delta x. And these are going to be the heights of the function. Okay, so if you wanted to use right intervals, we would use the numbers to the right. We would skip this 25, we would not include it, and we just use 31, 35, 43, 47, 46, and 41. Those are right intervals because you're using the speed at the end of the 5 seconds. So let me show you that calculation. Okay, for the right intervals, I would do 31 times 5 plus 35 times 5, 43 times 5, 47 times 5, and so on. Now notice a shortcut to this would be 5 times, then you just add all these numbers together. This 31, 35, 43, 47, 46, and 41. So if you add those together and then take that sum and multiply by 5, that is a shortcut to this calculation. Now notice we used the right endpoint, so that's at the end of the time interval. This may be an overestimate, okay, because notice it went from a smaller velocity to a larger velocity. So the velocity is increasing for most of these, except for these last two. So it's probably an overestimate. If I wanted to use the left sums, I could probably get an underestimate. For the left sums, I would do 25, because that's the left side of my velocity, added together with 31, 35, 43, 47, and 46. I would ignore this last time because I'm using the beginning velocity for my time interval. Let me show you those calculations. So the left sums, you would get 25 times 5 plus 31 times 5, 35 times 5, 43 times 5, 47 times 5, and 46 times 5, okay, which is 1,135. Now again, you could save the multiplying by 5 till the end and just add together these numbers here, 25 through this 46. We're ignoring the 41 because that is the right side of that time interval. So that would not be included. Okay, you can add them and then just multiply the 5 at the end. So we have 1,135. This may be an underestimate for that distance traveled, and this may be an overestimate, but they will be pretty close. If you wanted to average these two numbers, it may be a better estimate, okay? But it's hard to tell because the velocity is varying. It's not constantly increasing or constantly decreasing. It's increasing and then decreasing. So that's it for this lesson. Make sure you do your homework and let me know if you have any questions.